China just activated a thorium reactor that changes everything about nuclear power, and yes, the US is genuinely shocked. While the world was distracted, China solved a problem that's haunted engineers for 60 years. You're about to see how a 2-megawatt reactor sitting in the Gobi Desert just proved that everything we thought we knew about nuclear energy was wrong. This isn't hype, this is the moment thorium went from scientific theory to operational reality. But to understand why this reactor is so revolutionary, you need to see what's actually happening inside it. You're standing in Wuwei, in China's Gansu province, staring at a facility that looks deceptively ordinary. But inside this building is the TMSR LF1, the thorium molten salt reactor, liquid fuel. And the moment you understand what liquid fuel means, everything changes. Because here's what makes this impossible. The fuel isn't solid. It's not uranium rods sitting in water like every other nuclear plant you've ever heard of. The fuel is molten, a liquid salt heated to over 1100 degrees Fahrenheit, flowing through the reactor like glowing honey. And dissolved in that salt is thorium, the element that's about to rewrite the rulebook. Traditional reactors use solid fuel rods. They sit there, getting hot, and you cool them with water under massive pressure. If the cooling fails, those rods melt down Chernobyl, Fukushima, 3 Mile Island. But China's reactor? The fuel is already molten. It can't melt down because it's already liquid. It's like asking water to get wetter. The reactor vessel itself is roughly 16 feet tall, surrounded by heat exchangers and pumps that keep the molten salt circulating. The entire system runs at atmospheric pressure, meaning there's no pressure building up, no risk of explosive failure. You could walk away from this reactor, cut the power completely, and it would safely shut itself down. But here's where it gets wild. This reactor doesn't just avoid meltdowns, it actually uses its fuel efficiently. Inside that flowing liquid salt, something extraordinary is happening, something that sounds like science fiction but is pure physics. You start with thorium-232. It's not fissile on its own, meaning it won't split and release energy just sitting there. But when a neutron hits it, that thorium atom absorbs it and transforms into uranium-233. And uranium-233? That will split. That will release massive amounts of energy. So picture this. Liquid salt flowing through the reactor core at 1300 degrees Fahrenheit. The thorium dissolved in that salt is constantly absorbing neutrons and becoming U-233. The U-233 splits, releasing heat and more neutrons. Those neutrons hit more thorium. The cycle continues. The fuel is literally breeding itself as it burns. In a traditional uranium reactor, you use maybe 3 to 5% of your fuel before the rods are spent and have to be pulled out. The rest just sits there as waste. But in China's thorium reactor, you're using 99% of the fuel. 99%. You're squeezing nearly every ounce of energy out of the thorium because the liquid fuel cycle keeps converting and burning it continuously. And because the fuel is liquid, you don't need to shut down to refuel. Conventional reactors have to stop, cool down, open up the core, swap out fuel rods, a process that takes weeks. China's reactor? The salt just keeps flowing. You can add thorium while it's running. You can remove waste products while it's running. But the engineering challenge to make this work was absolutely brutal. Here's what stopped every other country from building this reactor. The salt eats everything. Molten fluoride salt at 1300 degrees Fahrenheit is one of the most corrosive substances you can create. It's not just hot, it's chemically aggressive. It attacks metal at the molecular level. Pump it through steel pipes and, within months, those pipes develop cracks, weaknesses, failures. The entire reactor becomes a ticking time bomb. The United States actually built a test thorium reactor back in 1965 at Oak Ridge National Laboratory. It ran for 5 years, and then they abandoned the entire program, not because the physics didn't work, but because they couldn't solve the corrosion problem. The materials technology didn't exist. Every valve, every pipe, every surface touching that molten salt was slowly being destroyed. For 6 decades, that's where thorium died. Everyone knew the reactor design was brilliant. Everyone knew thorium was abundant and safe. But nobody could build a reactor that wouldn't corrode itself into failure. China looked at that 60-year-old problem and decided to solve it with materials science that didn't exist when America gave up. They developed specialized nickel-based alloys, modified versions of Hastelloy N that could withstand the chemical assault. They optimized the salt chemistry itself, adjusting the mixture to reduce its corrosive properties without sacrificing performance. They built pumps with ceramic components and seals that could handle the temperature and chemical environment. They tested graphite moderators that could survive years of neutron bombardment while bathed in molten salt. It took them over 20 years of research, 20 years of testing, individual components, measuring corrosion rates down to the micron, rebuilding and refining. They didn't just build a reactor, they invented an entire materials ecosystem that could survive inside it. And when they finally assembled the TMSR LF1, something remarkable happened. The reactor came online, and engineers watched the temperature climb. 600 degrees, 800, 1100. The molten salt began flowing through the core, glowing orange hot, carrying thorium through the neutron field. The fission reactions started. Heat poured into the system. And then, they tested the one feature that makes this reactor fundamentally different from anything before it. They cut the power. In a conventional reactor, losing power is catastrophic. The cooling pumps stop, the water stops flowing, the fuel rods keep generating heat from radioactive decay, and without cooling, they melt. You have minutes, maybe hours, before disaster. That's why backup generators and emergency cooling systems are everywhere. That's why failures are so terrifying. But in China's thorium reactor, cutting the power triggers something elegant. The freeze plug melts. Here's how it works. At the bottom of the reactor sits a plug made of frozen salt, kept solid by active cooling. The moment power fails, that cooling stops. The plug melts. And gravity does the rest. The entire molten fuel load drains out of the reactor core into passively cooled dump tanks below. No pumps needed. No human intervention required. No backup systems that might fail. The fuel spreads out in the dump tanks, increasing surface area and decreasing density. The fission reaction stops. The decay heat dissipates naturally through the tank walls. The reactor is safe completely, passively, permanently safe. You could walk away and never come back. This is what engineers call walk-away safe. The laws of physics protect you, not complex machinery or human operators making split-second decisions. It's safety built into the fundamental design. But the real breakthrough wasn't just building it, it was proving it could actually run. China didn't just turn the reactor on and call it a success. They ran it and kept running it. 1,000 hours of continuous operation. That's over 40 days straight, with molten salt flowing at 1,300 degrees, thorium breeding into uranium-233, fission reactions generating heat. The entire fuel cycle operating exactly as designed. No shutdowns, no failures, no corrosion breakthroughs. Every hour that reactor stayed online, it generated data that nobody else in the world has. Temperature stability across the entire salt loop. Corrosion rates on every surface touching the fuel. Pump performance under continuous operation. Heat exchanger efficiency. Fuel breeding ratios. Waste product accumulation. The graphite moderator, which everyone said would degrade too quickly, held up. The nickel alloy pipes showed corrosion rates so low, they're projecting decades of operation. The pumps cycled millions of times, without seizing. The control systems maintained stable temperatures, even as fuel composition slowly shifted from thorium to uranium-233. And here's what that 1,000 hours proved. This isn't a laboratory curiosity anymore. This is a functioning power reactor. China's already designing the next version, a 100-megawatt unit. Not 2 megawatts, 100. That's enough to power a small city. They're using every data point from those 1,000 hours to refine the design, to improve the materials, to optimize the fuel cycle. They've moved past can we build this to how do we scale this? Because that's what the TMSR LF1 really is. It's the proof. Thorium reactors aren't theoretical. They're not 40 years away pending some magical breakthrough. They exist. They work. They've operated continuously for over 1,000 hours without the problems that killed every previous attempt. The reactor sitting in Wuwei just answered a 60-year-old question with operating data instead of promises. And now China has something nobody else does, a functioning blueprint for thorium power, backed by real-world performance that you can't argue with. The US pioneered this technology in the 1960s and walked away. China picked it up, solved what seemed unsolvable, and built what everyone said was impossible. That reactor isn't just running, it's rewriting what nuclear power can be.